Hey everyone, welcome back to Calculus 2. This will be the third part of our Lecture 23 on sequences, series, and convergence. So initially I was going to have this be two separate lectures, but then I combined them into one, and then as I was going through it I realized that this is much longer than a normal lecture, so that's hence the need for three separate videos on this topic. So previously we discussed sequences and convergence. What is a sequence? What does it mean for a sequence to converge? And now we want to shift our focus to series and convergence. So let's jump into it. So we would say that, an important application of, infinite sequences is in representing infinite sums. Well, infinite summations, better say. Okay, and so if A of n is a sequence, okay, so if A of n is a sequence, then the sum from I equals, so from n equals 1 up to infinity of A of n is an infinite series. Okay, so basically you've got sequences and series. A sequence is just the the list of numbers itself, and a series is then the infinite summation of the sequence. Okay. So basically the idea here is, n equals 1 to infinity of A of n is equal to A of 1 plus A of 2 plus ... plus, of course, A of n is in there, plus ... all the way up to, unending sequence here, unending summation here. Okay. So what we're going to be interested in for this section and the coming sections as well is trying to figure out when is an infinite series, when does an infinite series converge, when does it not converge, and in each case, in the former case, what does it converge to, right? i.e. what is the sum. Okay, so there's going to be a little bit of work that we'll need to do to get to there, but that's where we're headed. So to find the sum of an infinite series, we usually consider the following sequence of partial sums. Okay, this is a rather ingenious way to go about this. So s of 1 is equal to a1. S of 2 is equal to a1 plus a2. Right? And then the nth partial sum, these are called partial sums. So the nth partial sum is equal to a1 plus a2 plus ... plus a of n. Okay, so these are called partial sums. The first partial sum, the second partial sum, the nth partial sum. Now, inevitably, invariably, we will be interested in the nth partial sum more than the others. Right? So the idea here with the sum of an infinite series is basically like if this sequence of partial sums, so if the sequence of partial sums s1, s2, ... sn, ... right? If that sequence of partial sums converges, then the series is said to converge. Okay, and it'll have the the sum indicated in the following, and we'll define it in a second, right? So here's the idea, right? So you're given some kind of you've got some kind of an underlying sequence, A of n. Okay, from A of n, you can set up a series, right? So basically just the sum of all of the terms of the sequence. Okay, looks like this, right? Of course, we're using sigma notation here, some of the summation notation that we picked up back in Calculus 1, I believe. Might have been Calculus 2, might have been beginning of the course, maybe. Right, and then the idea is, like, the question that arises is, when is this sum, this infinite summation, when does it have a finite sum, right? And that, what we mean by a finite sum is really the following, right? So it's, you have these partial sums. S of 1 would be the sum of just the first term. S2 would be the second partial sum, would be, you know, A1 plus A2, the sum of the first two terms. And then the most important one, of course, is the nth partial sum, which is the sum of the first n terms, so kind of a generalization of this partial sum idea. Now, if the sequence of partial sums converges, then the series is said to converge. Right? So you think about it, you can think of these partial sums as just another sequence. Okay? So let's crank out a definition here. All right, so this is just kind of all wind up here so far. So for the infinite series, sum of A of n, okay, the nth partial sum, that's what we're defining, is given by S of n equals A1 plus A2 plus dot 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 plus A of n. Okay. Now, if the sequence of partial sums, so if the sequence of partial sums converges, okay, you know, and we'll say if the sequence of partial sum converges to S, okay, then the series sum of A of n, okay, converges to S as well. Okay. Okay, now, you know, so the terminology here is important. The limit here of the sequence of partial sums, right, we've denoted as S. The limit is called the sum of the series. Okay. All right, and so then the alternative would be, you know, if S of n does not converge, all right, then the series diverges. Okay. All right. So that's a little bit of a mouthful there, right? So for the infinite series, sum of A of n, the nth partial sum is given by the sum of the first n terms. If the sequence of partial sums, S1, S2, S dot 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 dot, Sn, dot 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 dot, continuing infinite sequence, if that sequence of partial sums converges to some number S, then the series also converges to S. Okay. The limit of the sequence of partial sums, that's our S, right? And we frequently will just refer to that as the sum of the series, right? That's the number that the series adds up to. Okay. If the sequence of partial sums does not converge, then the series will diverge, right? So if the sequence doesn't converge, then the series will basically grow indefinitely, right? Will basically grow without bound. Okay. All right, so this is all very interesting stuff. This is the opening of this section on series. Let's take an example here. Let's do an example. So consider this series, sum of from n equals 1 up to infinity of 1 over 2 to the nth power. Okay, so you can see what these terms look like. It's 1/2 plus 1/4 plus 1/8 plus ... right? And so let's think about what the partial sums here would look like. So S1 is going to be 1/2. S2 is going to be what? 1/2 plus 1/4. Right, and so that's going to be 3/4. S3 would be 1/2 plus 1/4 plus 1/8. Right, and so that one's going to be 7/8. Okay, and so on. Right, and then Sn, it turns out that Sn, which would be equal to 1/2 plus 1/4 plus 1/8 plus ... plus 1 over 2 to the n. It turns out that that is going to be equal to 2 to the nth power minus 1 over 2 to the nth power. Okay, now you may be saying to yourself, whoa, whoa, whoa. You know, where did this come from? Okay, well, this is basically based on the idea of the geometric series. So this is the geometric series, an example of the geometric series. There's an infinite variety of geometric series, but this is one such example. And we'll get into that in a second. But for now, you know, let's just roll with this. So this is the geometric series, which we'll discuss in a minute. Right, but for now, what we can say is that the nth term of the sequence the sequence of partial sums, the nth term of that sequence is 2 to the nth power minus 1 over 2 to the n. Okay, now what we need in order to determine whether this series converges, whether it has a finite sum, what we need to figure out is, does this sequence S of n converge? Okay, and so what's involved in that? Well, this is where we fall back on what we've discussed already, right? And so what we would need to show, well, for now, we can just use the limit of f of x equals 2 to the x minus 1 over 2 to the x, right? We can use that. And basically what we can see here is that, the limit as x goes to infinity of 2 to the x minus 1 over 2 to the x, well, that's basically equal to, you can kind of break up that numerator, it's equal to the limit as x goes to infinity of 2 to the x over 2 to the x minus the limit as x goes to infinity of 1 over 2 to the x. Right now, obviously, this is going to be equal to 1, and then this is gonna head to 0, right? And so what we can see is that this limit here is equal to 1, right? And so the sequence of partial sums, okay, we'll just denote it as S of n, converges to a value of 1. Okay, so S of n goes to 1 as n goes to infinity, and so that implies that the series I equals 1 to infinity of 1 over 2 to the n also converges, and the sum of this infinite series is 1. Okay, so that's the basic idea, right? So series is based on sequence, not only in the sense that the terms of the series are can typically be thought of as the terms of a sequence, but also because in order to identify convergence of a series, you have to consider another sequence, which is the sequence of partial sums, right? This S of n sequence. And if the sequence of partial sums converges, then whatever it converges to is also the sum of the infinite series. Okay, so it's a little bit. There's a little bit of intricacy here with the relationships, but hopefully that's coming through. Hopefully that's coming through. Let's take and work another example. Okay, so here's another example. Consider the series. Okay, so this is n equals 1 to infinity of 1 over n minus 1 over n plus 1. Okay, so you're basically taking 1 over n and subtracting off of it what would naturally be sort of the next term. Okay, in a 1 over n sequence. Okay, so what does this look like? Well, sum of n equals 1 to infinity of 1 over n minus 1 over n plus 1. Well, the first term, when n is equal to 1, you're going to get 1 minus a half, right? All right, if n is 1, that's a 1, and that's a 2, so 1 minus a half. The second term is going to be 1 half minus a third, and then a third minus a fourth, and so on, right? And so we can kind of rearrange this a little bit and get some sense for what's happening. Kind of basically just drop the parentheses. So what if we look at it like this? 1 minus a half plus a half minus a third plus a third minus a fourth plus 1/4 minus a fifth plus ... right? Right, so you can see that there's a lot of cancellation happening here, right? So there's a lot of cancellation happening here. Let's think about S1. S1 is equal to just 1 minus a half. What about S2? Well, S2 is 1 minus a half plus a half minus a third, right? So what does that really mean? Well, it means it's 1 minus a third. What about S3? S3 is 1 minus a half plus a half minus a third plus a third minus a fourth. Right, so you can see these two cancel out, those two cancel out, so you get 1 minus a fourth. Okay, so there's a definite pattern here. The first term is 1 minus 1 over n plus 1. The second term is, the second partial sum is 1 minus 1 over 2 plus 1, right? So you can see the pattern here. So the nth term is going to be 1 minus 1 over n plus 1, isn't it? Right? So this is the nth partial sum. What happens to the sequence of partial sums? All right, what happens to this as n goes to infinity? Well, again, kind of falling back on what we talked about in the previous section with sequences, we're just going to need to look at the limit of the function x. So the limit as x goes to infinity of 1 minus 1 over x plus 1. What happens here? Well, this is pretty straightforward. So you're going to have the limit as x approaches infinity of 1 minus the limit as x approaches infinity of 1 over x plus 1. Right, so this one is 1, and that one goes to 0. So this is equal to 1. Right? So that means Sn goes to 1 as n goes to infinity. So the sequence the series itself will also converge, right? And it'll specifically converge to whatever the partial sums converge to. So the series n equals 1 to infinity of 1 over n minus 1 over n plus 1 will sum up to 1. Okay. Right, so that's pretty interesting, right? Because if you think about what's happening here, this one is sort of intuitive to see, right? So the nth term is 1 minus 1 over whatever, basically whatever n is, right? So if n is infinity, then the part you're subtracting off here is going to be basically 0. So the larger n gets, the piece that's being subtracted from 1 is getting smaller and smaller, right? And so specifically in the limit, this is 0. Right, so it's identical to 0, right? So then, the sum just basically becomes 1, which is what we see down here. Okay, this is an example of what's called a telescoping series. Right, specifically this behavior of kind of adding something, subtracting it, adding, subtracting. Okay, it's going to have the form. Let me flip pages here. So a telescoping series will have the form. So like b1 minus b2. Bn rats. Sum n equals 1 to infinity of bn minus bn plus 1, right? Which would be like b1 minus b2 plus b2 minus b3 plus, and so on, right? Right, so the terms kind of subsequently remove one another. Okay, so for a series like this, so for telescoping series, basically S of n is going to be equal to b1 minus b of n plus 1. Right? That's kind of the way it's going to work out. Okay, so the telescoping series, when it has this form, will converge if and only if b of n approaches a finite number as n goes to infinity, right? So these will converge if and only if, right? If and only if bn approaches a finite number, right? As n goes to infinity. Okay. So if the series converges, they will converge to, basically S equals, whatever B1 is plus whatever B1 is plus the limit as n goes to infinity of Bn plus 1. Sorry, minus the limit. Right. So if a telescoping series converges, it's gonna do this. Okay. Right. And so what's important here is obviously this is going to be a finite number. What's important is what happens here with that last term. So in the example we saw, the last term, the limit was 0. Right. So that the piece you're subtracting off basically diminishes to 0. In the limit, right? Hence the conversion. Okay, here's another example. Let's try to find the sum of n equals 1 to infinity of 2 over 4n squared minus 1. Okay, so we'll say this is, so the nth you know, S of n here, oh sorry, A of n is equal to what? Well, it's given, right? 2 over 4n squared minus 1. S of n is not given. A of n is given, though. Now we can do some. This is not terribly helpful in itself, right? Let's do a partial fraction decomposition on this. Right, so using kind of a partial fraction decomposition, we can see that A of n equals 2 over 4n squared minus 1 is going to be equal to, and you can just do this factoring quick, 2n minus 1 times 2n plus 1. Right, and then it turns out that if you were to do partial fraction decomposition on this, you would get 1 over 2n minus 1 minus 1 over 2n plus 1. Now, it takes a little bit of work to go from here to here, but we know how to do this. All right, it's a partial fraction decomposition. Okay. Now, once you've done that, right? Once you've done that, then you can see something pretty clearly. The nth partial sum looks pretty straightforward. So S of n would be equal to 1 over 1 minus 1 over 3. That's the first term, plus 1 over 3 minus 1 over 5, right? Just kind of adding, you know, 2 times 2 is 4, plus 1 gives you the 5. 2 times 2 is 4, minus 1 gives you the 3. Right, and so you can see that this is basically doing, you know, what you would expect from a telescoping series. Okay, and then at the end, of course, is the 1 over 2n minus 1 minus 1 over 2n plus 1, right? So this is kind of what the nth term looks like, the nth partial sum, sorry. And so what happens here? Well, I mean, just looking at this closely, you can see the 1/3 and the 1/3 are out, the 1/5 and the 1/5 are out, the 1/7 and the 1/7 are out. Basically, everything is out, and the nth term, so the nth partial sum, would be basically 1 minus 1 over 2n minus 2n plus 1. Right? Everybody can see that, I hope. So basically, all of the terms in the middle will basically undo one another, right? And so the series will converge, and specifically, it'll converge to, you know, what is it going to? It's going to be S equals b1 minus the limit as n goes to infinity of b of n plus 1, which in our case is 1 minus the limit as n goes to infinity of 1 over 2n plus 1. Right? And what is this? Well, this will be 0, right? That's going to turn to 0, and so the whole thing is going to converge to 1. Right? So the series converges, and the sum is 1. Okay, so specifically we found the sum of this, n equals 1 to infinity of 2 over 4n squared minus 1. That's 1. Okay, so I think, you know, sometimes when people see something like this, they immediately think to themselves like, well, this is a constant over 4n squared minus 1. This is gonna go to 0, right? The denominator is going to grow really quickly and going to go to 0. That's not the way to think about it. The way to think about it is, you know, 1, find the nth partial sum, S of n. 2, does S of n converge? Okay. It's not about whether or not A of n converges, it's about whether or not S of n converges. Okay. All right, very good. Let's take a pause here and talk about geometric series. All right, we saw an example of that a few minutes ago. We kind of glossed over it, but let's talk about it now. So our first example, what was it? It was sum n equals 1 to infinity of 1 over 2 to the n. Our first example was this, and this is a geometric series. Okay, so the question is, what do we mean by a geometric series? Well, geometric series has the form basically like this: n equals 0 to infinity of a times r to the nth power. Okay, and so this is going to be equal to a plus ar squared plus dot dot dot, right? Plus ar to the nth power plus dot dot dot, right? And so and kind of, sort of implicit here is that a is not equal to 0, right? If a is 0, then this becomes very uninteresting. Now, with a geometric series, this r, whatever r happens to be, is very important. So r is frequently called the common ratio. The common ratio of the series. Okay, and it's it's common to all of the terms, right? It's called the common ratio. Now, what can we say about geometric series? Well, we can say something very precise about geometric series, actually, and we've got a nice theorem. So a geometric series with ratio r diverges if the absolute value of r is greater than or equal to 1. Okay. If if the ratio is between 0 and 1, if 0 is less than the absolute value of r, which is less than 1, then the series converges to the sum. Now here it is, so it's n equals 0 up to infinity of arn, and it's gonna, so whenever r, an absolute value, is between 0 and 1, the series will converge to a over 1 minus r. Okay. So that's very nice, and that's what we saw in our initial example. Okay, that's what we saw in our initial example. So we'll come back to that. But first, let's walk through the proof of this. This has got a nice, clever proof, which is kind of a staple of Calc 2. So let's talk about this for a second. Okay, so let's assume. First of all, we'll assume that r is equal to plus or minus 1. Okay, so it's plus or minus 1. Then S of n is going to be equal to, of course, a plus ar squared plus dot 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 plus ar to the nth power. Right, and we can factor the a out, so it's equal to a times 1 plus r squared plus dot 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 plus r to the nth. Right? And so that means, well, since r is 1 or negative 1, that's going to basically mean that that the nth partial sum is equal to a times, basically plus or minus n, right? There's n of them here. Okay. And, right, so then the limit as n goes to infinity of, plus or minus n, a times plus or minus n, would be equal to infinity, right? So obviously It's going to grow without bound there, right? And that basically means that the series will converge or diverge. Okay, so that's that first case when r is plus or minus 1. Let's next assume that r is not equal to plus or minus 1. Okay, so let's assume next that r is not equal to plus or minus 1. Okay, so then S of n is equal to a plus ar squared plus dot 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 plus arn, ar to the nth power. Minus 1. It should be minus 1 there. I think it should have been minus 1 on the previous discussion as well, but okay. Right, so you've got ar to the n minus 1 here. And so let's multiply both sides by r. So you'd have r times S of n is equal to ar plus ar squared plus dot 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 plus ar to the n, right? Just multiplying both sides by r, right? So basically each of the exponents on the r just bumps up 1. So your last term would be ar to the nth power instead of ar to the n minus 1 power. Okay, now if we subtract, one from the other, we get S of n minus r times S of n, right? So this minus that is this. And that's going to be equal to, well, let's write it out. So it'll be a plus ar plus dot 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 plus ar to the n minus 1 minus, and then this one would be ar plus ar squared plus dot 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 plus ar to the n. Now what's going to end up happening here? Well, you're going to have the a, but then the ar minus ar, and then there's going to be an ar squared minus ar squared, right? And everything's going to, all the middle terms are going to back out of this, and it's going to be a basically minus ar to the nth power, right? Which will be equal to a times 1 minus r to the nth power, like so. Okay, so what I have now is S of n times 1 minus r is equal to a times 1 minus r to the nth power. Okay, and so that means the nth partial sum is equal to 1 minus r to the n over 1 minus r. Oh, sorry, I need the a on there too. Yeah. Okay, all right. Okay, so we're almost there. Almost there. So we've got S of n equals a times 1 minus r to the n over 1 minus r. That's what we're that's where we got to previously. So now let's talk about, so we know that r is not positive or negative 1, right? So if 0 is less than r, which is less than 1, so basically r is between 0 and 1 in absolute value. If that's true, right, it follows that r to the nth power goes to 0 as n goes to infinity. Okay, and in that case we'd have, right, basically the limit as n approaches infinity of S of n will be the limit as n approaches infinity of a times 1 minus r to the n over 1 minus r. All right, so let's think about what this is. All right, so this is equal to a times 1 minus r. We pull that out. Okay, pulling that piece out, and then what we're left with is 1 minus r to the n, right? And so basically what we're showing here is why does, what we know that r to the n will go to 0, right? But what happens in the limit in total, right? And so this is going to go to 0, right? So this would be 1 minus r, because remember, r is a negative number, or sorry, r is a fraction. R is a fraction, right? It's between 0 and 1, right? So when you exponentiate it and that exponent goes to infinity, then this whole piece here. Oh, sorry, I do need to break it up first. My bad. I apologize. A over 1 minus r. So this really would be broken up into limit as n approaches infinity of 1 minus the limit as n approaches infinity of r to the n, right? So this piece would go to 0. This piece obviously goes to 1. And so you get a over 1 minus r as your limit. Okay. Right? And then when r is larger than 1, the reverse is going to happen here, isn't it? Right? So it's just like exponentiating, the number 10, right? As 10 to the n, whatever r happens to be when you exponentiate it increasingly, right? The whole thing tends to 0 or tends to infinity, right? So in that case, the series would diverge. Okay. All right, perfect. So that's the proof. That's the proof of the geometric series, the convergence of the geometric series. Let's do an example using that. All right, it'll be a lot like the first example that we looked at. So does the series n equals 0 to infinity of 3 over 2 to the n converge? And if so, obviously, what does it converge to? Well, this is, let's kind of break this thing down a little bit. We can see that this is basically just a riff on the original example. The original example is 1 over 2 to the n, but 3 over 2 to the n, right? Well, that's basically going to be, if you want to break it up, this would be n equals 0 to infinity of 3 times 1 over 2 to the n. Okay, right, so you can think of this as 3 times 1 plus 3 times a half plus 3 times a half squared plus dot dot dot. Right, so a is equal to 3, r is equal to 1/2. Okay, and so basically, 0 is less than the absolute value of r less than 1. Right, so r is a half, right, so it's right in between. So because of this, the series will converge. Okay, so the series will converge, and specifically it'll converge to s equals a over 1 minus r, which in this case is 3 over 1 minus a half, otherwise 3 over a half, which is 6. Okay, so in this case, this series converges to 6. The sum of this infinite series is 6. Okay, very cool. Another example. Infinite geometric series is extremely important throughout mathematics. It comes up in all branches and comes up pretty commonly, actually. So let's take another look. Let's look at another example. So here we're going to use a geometric series to express 0.080808, repeating forever, the 08 piece, 08, 08, 08, 08. Right, so we want to use a geometric series to express this. We basically want to express this as an infinite sum, okay, as an infinite summation. Right, and so we can start by just noting that 0.080808, right, repeating can be written as, and you got to be a little bit clever here. This is 8 over basically 10 squared, right? 0, 0, so 10 squared plus 8 over 10 to the 4th, right? That gets you that one, plus 8 over 10 to the 6th, plus, and so on, right? We could do this forever, right? And so this is kind of an infinite series in its own, right? So what we could, the way to basically re-express this so it fits the geometric series would be to write Right, so basically this can be re-expressed as, right, so we could say the sum n equals 0 to infinity of 8/10 squared, 8 over 10 squared, times 1 over 10 squared to the nth power. Right, now notice, right, let's write the first couple terms out here. So when n is equal to 0, this is 8 over 10 squared. And then if this is all 0, that's just times 1. What happens when n is equal to 1? Well, then it's 8 over 10 squared times 8 over 10 squared. When n is equal to 2, it's 8 over 10 squared times 8 over 10 squared. Oh, sorry, this should be a 1 here. These should be 1. We don't want to square the 8 each time, right? We don't want to exponentiate the 8, just the 1. Okay, right, and so then, and then obviously on and on, right? But then you can see that this is just 8 over 10 squared. This is 8 over 10 to the 4th. This is 8 over 10 to the 6th, and so on, right? And you'll catch basically this. All the terms will align with this. Okay, and so this sum, n equals 0 to infinity, of 8 over 10 squared times 1 over 10 squared to the nth power. It can be written like what we just looked at, but you could pull the 8 over, well, basically the question is whether or not this converges, and what does it converge to? Right, so we're probably going to want to say that it converges to this, right? Obviously, because that's what it's built on. But let's use the properties from the geometric series that we just discussed. So here, a would be equal to 8 over 10 squared, and your r is equal to 1 over 10 squared. Okay, so clearly this is the r is between 0 and 1, right? So clearly this is going to converge, right? But what does it converge to? Let's show that it does what we want it to do. So n equals 0 to infinity of 8 over 10 squared times 1 over 10 squared to the nth power. Well, it's supposed to be equal to a over 1 minus r. So let's see here. 8 over 10 squared divided by 1 minus 1 over 10 squared. Right? Does that look right? Well, what we end up with here is 8 over 10 squared divided by, well, this is going to be 100 minus 1 over 100. So basically 99 over 100. Okay. And what do we end up with there? Well, you do the division there, you're going to basically get 8 over 99. Right? Now when you plug 8 over 99 into your computational aid, your calculator, then this will spit out this number. Right? So this is a way to express this real number as a rational number. This is a rational number, but in terms of a ratio of integers. And so there you go. There we go. So we've shown that this repeating decimal number can be written as a geometric series. Okay. All right. Very good. Very good. Let's talk about some properties of series. So series in general. So we'll say if the sum of a of n is equal to a, and the sum of b of n is equal to b, and c is a real number, then we've got the following, right? So you got two series, a, you got, a of n and b of n. Those two series, they both converge to some finite numbers a and b. And so what are the properties that hold here? So the nice ones all hold. So c times a of n, so any real number constant times the terms of the series is going to be equal to c times whatever the series converges to the sum of the infinite series A times basically the real number C. Okay, so that's what you'd expect and hope to see. If you've got the series and you're summing the terms, A of n plus B of n, well then logic would say, and intuition would also agree that that's equal to A plus B. And the same thing is true for the differences. Right, if you got A of n minus Bn, and those are the terms, then that's equal to A minus B. All right. Okay, very good. Okay, so those are some properties, right? And these properties are extremely easy to prove, right? So I'll just leave it to you guys. But these are things that'll take about 5 minutes to prove. You basically just have to expand the series, combine them, right? You know, start with this, write the terms out, reorganize the terms, and recompress them, and you'll see that, oh, it's A plus B. And same thing with this, same thing with that. Very easy to show that those properties are true, just using basic notions about sums. How about a theorem? Okay, this theorem is goes as follows: if the series n equals 1 to infinity of A of n converges. Okay, so if the series converges, then the limit as n goes to infinity of A of n must be equal to 0. That's kind of a powerful, simple statement, but a pretty powerful one. So if the series converges, what that basically means is that the terms of the sequences must converge to 0. Okay, right. So if you're going to add up all these terms, then what needs to be the case is that the sequence itself needs to diminish to 0. Right, the terms of the sequence need to get smaller and smaller and smaller until they basically vanish. Okay. And this is one we can prove pretty easily. It's kind of a nice, I mean, it kind of gives you the connection, right, between these two. Right, so if the series has a finite sum, then that means the sequence must converge to 0. Okay, so let's assume for the proof, let's assume that the sum from n equals 1 to infinity of A of n converges. Right, and let's say that we'll say it converges to L. Okay, so it's going to equal some value L. Well, then we know that the limit as n goes to infinity of the nth of the partial sums must equal L. All right. Okay. All right. Then, okay, so then what we can say then, comma, because S of n is going to be equal to, basically, so the nth partial sum is equal to the n minus 1 partial sum plus the last term, right? Right, so this is not meant to be cryptic or weird, but, you know, a lot of times this can kind of throw people. So what do we mean by this? Well, S of n minus 1 is equal to a of 1 plus a of 2 plus dot 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 plus a of n minus 1. S of n is equal to a of 1 plus a of 2 plus dot 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 plus a of n minus 1 plus a of n. So all this is saying is that, hey, look, this is equal to this plus that, right? This, I mean, they'd be the same except for this last term. Right, so S of n is equal to S of n minus 1 plus A of n. Okay, and so, well, so we've got this, right, this, and, well, we need one more thing here, and the limit as n goes to infinity of S of n is equal to the limit as n goes to infinity of S of n minus 1, right, which is equal to L, right? So we know that too, right? So the limit of the nth partial sum, you know, if you take that term, it's got to be equal to the n minus 1 partial sum term as well, right? Just that addition of that plus 1, it's not gonna change the limit, right? So both of these are equal to L. Okay. Okay, so you got kind of these two pieces here that are important. Right, so those two pieces taken together. Okay. Okay, so because of those, it follows. Right, it follows that what? Well, L is going to be equal to the limit as n goes to infinity of s of n, which is equal to the limit as n goes to infinity of s of n minus 1 plus a of n, right? That's just this up here, right? So taking the limit as n goes to infinity of s of n, right, which is the same thing as this, right? It's broken out there as well. And we can break this apart here. So this is the limit as n goes to infinity of s of n minus 1 plus the limit as n goes to infinity of a of n. Okay. Now we know that that's L, right? So it's L plus whatever this limit is. Okay. Right, so then what happens? Well, what we have then is that the limit as n goes to infinity of a of n plus L, so this plus this is equal to this. Right? So it just kind of falls right out of there. So that means that the limit as n goes to infinity of a of n must be 0. Okay? So it just kind of falls right out. Right? Now this may seem a little bit like some funny, some funny calculations or some hand wavy kind of stuff, but all of these notions are very, very clearly true, right? Right. So the key one here to notice is this and this, right? These two pieces that I boxed in here. So this is obviously true. This is just by definition. Just by definition, right? The only thing that separates the nth partial sum and the n plus n minus 1 partial sum is just this one term a of n. There's nothing mysterious or strange there. This piece here, right? So this we assume that the sum converges, the series converges, and so that means this is equal to L, this part. Now, this one you may have to think about for a second, but this is also quite clearly true, right? It's just, you can think of it as almost just a substitution of variables kind of argument here. Instead of n, you've got n minus 1. But in the limit, that doesn't matter, right? In the limit, we usually talk about the nth partial sum when we're trying to find the convergence, because it's simply the easiest way to write it. But it doesn't really matter if you represent it as the nth partial sum or the n minus 1 partial sum. They both are basically the same, right? And they both equal L in the limit. Okay, so those two things together, then you can just string together this nice little equation, right, which forces out that the limit must be 0. Okay, so a nice little proof, kind of a powerful proof, shows you a lot of, kind of helps you to get more of a visceral sense for why and when series converges and how it relates to the underlying terms of the sequence, right? So basically, a series will converge if, a series converging implies that the terms of the original sequence have to converge to 0. Okay. One more theorem here. Okay, this is going to be frequently called the nth term test for divergence. Nth term test for divergence. Right, so basically this is kind of like the flip side of what we just talked about. Right, so basically this says that if the limit as n goes to infinity of a of n is not equal to 0, well, then this is basically the contrapositive. Then that's going to imply, this is the contrapositive of the previous theorem, so that's going to imply that the series n equals 1 to infinity of a of n diverges. Okay. So this is the contrapositive. Basically, you can think of it as the opposite statement. So it's the contrapositive of the previous. Right. So, you know, if you are asked to, hey, does this particular series converge? If you're able to look at the terms of that series and say, oh, they do, that sequence A of n does not equal 0 in the limit, then that implies divergence in the series. Okay. Right, so a couple simple examples of kind of showing that. You know, consider this one, n equals 0 to infinity of 2 to the n. Right now, does this series converge? Of course not, right? Of course not, because the limit as n goes to infinity of 2 to the n is clearly infinite. Right? That's going to imply that n equals 0 to infinity of 2 to the m diverges. Right, obviously infinite as well. Right, if your terms of the sequence are growing without bound, then certainly when you add them together, they're going to grow without bound as well. All right. What about this one? Mm, 2n factorial plus 1, we'll say. Okay, so you got factorials here. Does this series converge? Well, let's see. Let's consider the old trick. All right, we'll just look at the terms of the sum here, right? So, so if we have n factorial over 2n factorial plus 1, we could divide everything by n factorial. So you got n factorial over n factorial, and then 2n factorial over n factorial plus 1 over n factorial. Okay. And what do we get here? We get 1 over 2 plus 1 over n factorial, right? So what happens with this in the limit? So the limit as n goes to infinity of, you know, this thing that we just looked at here, this 1 over 2 plus 1 over n factorial. Well, these are fine, but this is going to 0. Right? So you get 1/2 here. Right? So what do we have here? So what we can say is that because the limit of the nth term does not equal 0, right? What does that mean? Because the limit of the nth term does not equal 0, the series must diverge, right? So a lot of times people will get this mixed up here. They'll say, oh, look, the terms of the series all, you know, they converge to 1/2. That must mean the series converges, right? No. The terms converge does not imply series converges. Only if the terms converge to 0 does that imply that the series converges. When the nth partial sums converge, that implies that the series converges. Right? So this is an, and this is s of n. Big difference. Really big difference there. Right, so if a of n converges, well, the series may or may not converge. If a of n converges to 0, you're good. That means the series must converge as well. If s of n converges, then whatever it converges to, the series converges as well. Okay, so sort of a subtle, well, it's not that subtle, but I mean, it's a little terminology. It's got to get used to that terminology. But okay, all right. So that's kind of an intro to series. And don't worry, we'll get into lots and lots of different examples and other aspects of infinite series in a moment, so, or in incoming lectures. But we're getting closer to the end of Calculus 2, and so keep up the hard work if you've made it this far. And next time we'll talk about the integral test, and we'll talk about something called p-series or harmonic series, better known as harmonic series by most. So we'll talk to you all then. Take care.